Hello everyone, I'm Donghyun Lee from Seoul National University. Today I'm going to present my work called FastPoint Accelerating 3D Point Cloud Model Inference via Sample Point Distance Prediction. This work is done with my colleagues at Seoul National University under the advisement of Jae Lee and Honghae Yoon. Since the release of PointNet and PointNet++, various 3D point cloud models have been proposed, enhancing the model performance and computational efficiency. They all share similar model architecture, utilizing set abstraction and feature propagation layers as core components. Despite prior advances, the irregular nature of point cloud data still poses significant computational challenges, limiting the practical deployment of 3D point cloud models in real-time applications. We have conducted latency breakdown on 3D point cloud model inference and identified that the two major performance bottlenecks are farthest point sampling and neighbor search. To address these bottlenecks, we propose two techniques: minimum distance prediction sampling, or MDPS, which accelerates FPS via sample point distance prediction, and redundancy-free neighbor search, which eliminates redundant distance calculations in neighbor search operations. First, we'll look at farthest point sampling. We make two key observations on FPS algorithm. The first observation is that the distance between the sampled points decreases as sampling proceeds, and this decreasing trend of minimum distance displays a smooth curve. We also observe that we can accurately estimate this curve using only a few initial FPS iterations. This allows us to achieve comparable sampling quality with FPS with low computational costs by simply sampling points according to the estimated curve. Based on these observations, we propose minimum distance prediction sampling. We train a low-cost MLP-based estimator which gets initial 1/10 of the minimum distance curve as an input, and outputs the rest of the curve using the training split of each point cloud dataset. Sampling starts by performing FPS for 1/10 of the total iterations and estimating the full distance curve using the estimator. Then, we divide the curve into multiple segments, perform ball query that identifies points within a radius of each segment boundary, and store the results to the corresponding exclusion lists. Finally, at each sampling iteration, points that are close enough to the previously sampled points are excluded based on the exclusion list, and we randomly sample from the remaining candidates. Through this strategy, the sampled points closely follow the estimated distance curve, achieving a sampling quality comparable to that of FPS. MDPS is much faster than original FPS because it only requires 1/10 of FPS iteration. Distance calculations in exclusion list construction are fully parallelizable, and the use of exclusion list eliminates the need for distance calculations while sampling. Next, we look at neighbor search. We observe that there are redundant distance computations across ball query, KNN, and distance curve segmentation of MDPS. For example, the distance between P0 and P7 gets computed several times, once in MDPS, again in KNN, and also in the ball query. Based on these observations, we propose redundancy-free neighbor search. For KNN, we can directly reuse the exclusion list to filter out the points that are too far away to be potential KNN neighbors. For ball query, we add extra exclusion list while sampling and use this list for ball query. Since distance between points are calculated only once regardless of number of exclusion lists, this does not incur significant latency overhead. We apply our techniques to state-of-the-art PointNet++ based models and evaluate the performance on NVIDIA RTX 3090 GPU. Our experiments demonstrate that FastPoint achieves geomean 2.55x end-to-end speedup with no impact on model accuracy. Thank you for listening to our talk. Please refer to the full paper for more details.